Many aspects of the world around us are exogenous to us in the sense that they are not affected by the actions that we take. As humans, we're quite good at figuring out which of these aspects we need to reason about in order to perform a particular task. Consider this robot tasked with cooking a meal in a kitchen. There are many aspects of the world that it cannot control, such as what's playing on TV, what the current time is, and what the weather is like outside. Some of these may matter to the task, and others might not. The goal of this work is to formalize the problem of learning which aspects of the exogenous state a robot should reason about, and to develop methods for addressing this problem. We can model the situation as follows. The state of the world can be split up into two components, xt and nt. Critically, the exogenous state xt has some influence on the agent's reward function, and so the agent must reason about it when trying to plan. We focus on the setting where the exogenous state space is extremely large, and the agent must learn which of these state variables xi are worth reasoning about. Accordingly, we use the term mask to describe a subset of these state variables. Formally, the mask learning problem is to find a subset x tilde of exogenous state variables that maximizes the expected returns of the policy pi tilde resulting from only thinking about the variables in x tilde. The second term is a regularizer that stops the mask from becoming too large. Without this term, it would always be optimal to have all variables be in the mask. The exogeneity of these variables means that, given a generative model, we can efficiently roll out simulations of these variables' dynamics without committing to any sort of policy, since by definition, exogenous variables transition independently of the robot's actions. Leveraging this, we develop an algorithm that we informally describe here. This algorithm is motivated by exploring the connection between the value functions of the reduced and the full model. In the first phase, we initialize our mask by estimating from data which variables directly influence the reward function. In the second phase, we greedily add variables that help us better predict the dynamics of the variables already in our mask, using the notion of mutual information. The remainder of this video qualitatively explores what the algorithm does in our experimental domain, with some example executions. This is a domain in which there are many agents executing their own fixed stochastic policies. For a robot to perform tasks in such a complicated environment, it will have to reason about what aspects of the state it can ignore for planning purposes. Even if we discretize the domain, there are 10 to the 80 states. However, much of the state is irrelevant to the robot's tasks. So let's walk through what our algorithm does in this domain. In the first phase, it estimates which variables directly influence the reward. The exogenous state variables in this domain are spatial features, i.e. an occupancy grid, attributes of the other agents in the world, such as their poses and velocities, which tables the objects are on, and the goal, which for our purposes will be an object that the robot must navigate to. We are assuming here a fully observed world. We note that exogeneity does not technically hold. The robot can affect the positions of other agents by getting in their way, but it's well worth making this assumption in such a complicated domain. So let's explore the impact that setting different goals has on the mask that our robot ends up learning. Our first goal will be for the robot to navigate to an object whose position is fixed. The reward function is 1 for finishing this task and a smaller negative penalty for colliding with any of the other agents. Which variables directly influence this reward function? Well, the occupancy grid is important because reasoning about it helps the robot avoid crashing. The placement of the objects matters too, because the robot is going to be trying to navigate to one of them. In this split-screen view, we show on the left the real world, and on the right the masked world, i.e. the reduced model that our robot plans in. Our gold and purple robot is trying to reach the green object on the top right table, which was randomly chosen to be the goal object out of it and the 2 red objects located elsewhere. On the right screen, the red squares on the ground describe which locations within a discretization of the environment the robot has chosen to consider within its mask. Out of these, the green circles denote locations that are currently occupied. Importantly, the robot has realized that because the only goals it could be given involve navigating among the tables, it need not concern itself with tracking occupancies within the bottom left quarter of the environment. There are many gaps among the red squares, which is due to the fact that we perform Monte Carlo estimates of variables directly influencing the reward, and so we may miss some. This can easily be addressed by increasing the number of samples used in the estimation. Notably, the masked world does not contain any other agents, just the spatial features and the objects, as can be seen on the right screen. Now, let's change the agent's goal. We will make the object it is trying to navigate to manipulable by some of the other agents. The reward function remains unchanged, but there is now another variable that is important for our robot to consider, the current pose and heading of the other agents that can move the objects it may be asked to navigate to. This will be captured by the second phase of our algorithm. Reasoning about those other agents and where they are heading will allow us to better predict the dynamics of the object placements on the tables. Focus on the right screen here. As the gold and purple robot makes its way toward the green object on the bottom table, this object suddenly disappears. This is the mask that our algorithm initialized in phase 1. It only includes variables directly influencing the reward function, and so the mask does not include information about the other agent that has actually grabbed this object, as can be seen in the real world on the left screen. So our robot sort of moves about randomly while it waits for the green object to reappear, which it eventually does on the top right table. Reasoning about this other agent would have helped our robot better predict the dynamics of the object locations. On the next iteration, the mask includes one of the other agents, as can be seen on the right screen. In this example, that other agent is manipulating the goal object. The difference in our gold and purple robot's behavior is apparent. As it was going down toward the green object on the bottom right table, it realized that the other agent will get there first and changed course, heading to the upper right table to wait for the other agent to bring over the goal object. This allows our gold and purple robot to obtain higher rewards due to the discount factor. We can see similar behavior in this example as well, where our gold and purple robot goes to the bottom table in anticipation of being delivered the goal object, which is only possible because our robot considered the other agent's movements within its mask. In future iterations, the algorithm will include more and more agents within its mask, until it reaches a stopping point. We have seen that setting different goals can have big impacts in the mask that our robot ends up learning, as we would expect.